Hello guys, welcome to my YouTube channel. Today in this video I'm gonna make you learn how to implement the logical operators, arithmetic operators and rational operators, equality, concatenation, replication, bitwise operators and reduction operators and shift operators as well. So these operators are the building blocks in FPGA programming, so I will let you know how to implement that in the quartus 15.
So first we will go to implement the arithmetic operators. These key symbols are like this, and these are the general operators that are used in our daily life. These are also called as the binary operations because they use these two digits to perform the operations. So these can perform multiplication, division, addition, subtraction, and taking the modulus. So first you have to just name the module as you have named your file, and then I'm taking the input of 4-bit value, that is A and B, and then taking the output of 8-bit value because the multiplication addition of the 4-bit value can sometimes exceed the 4-bit value and results in 8-bit value. For example, if I'm going to multiply 8 with 2, so it is 16, so 1 will occupy 4-bit and 6 will also occupy 4-bit, so it will become 8-bit. And then I'm going to assign all these values to the C, D, E, F, G. Here it is equals to A into B, and then A divided by B, and then A plus B, and then A minus B, and this is the modulus of A and
So
B.
now I'm going to simulate it and then click on the university VWF and then click OK and then go to the edit and then insert and then node and then node finder and then list. You have to just choose only the input groups and the output groups and then make it to appear on the graph. When all this happens, you should just click OK and then again OK. So you can see that the graph is appearing, so we have to just give the values of the inputs A and B just as they are appearing in this. So by mistake the wrong values that I've chosen because E, F, G, H, so I've chosen. Again, you have to just convert these values into unsigned decimal and then convert this only into unsigned decimal. Here you can repeat the same process for all these 6 in order to show the complete multiplication and addition, because there is the 8-bit value, because after multiplication it can exceed the 4-bit value and become 8-bit, so we will convert this into the 8-bit. And now I will go to run the simulation. It will take a little bit time. So here you can see the answer of this, because you know that multiplication of 12 and 3 is 36, and then division is 4, and then addition is 15, subtraction is 9, and then the modulus is 1. And then we will see its Rtl view. Here is the Rtl view for this. You can see there is division, addition, subtraction, multiplication, and then the modulus. These all have this 8-bit outputs and the 2 4-bit inputs. So coming towards the next circuit, here you will see that
these are the operators that equates the value, and if any of the one value will be equal to 0. For example, if A and B, for example, if A is equals to 2 and B is equals to 0, then AND logical operator means that logical AND operator will give the value 0 because one of the input is 0. Similarly, if logical OR, this is the logical OR operator, and if the logical A logical NOT, for example, if E is equals to A logical or B is equals to E, then it will evaluates to 1 because one of the value in these both inputs will be 0. Here the A is equals to 2 and B is equals to 0, then A means that 2 logical or B is equals to 1. And similarly, this is the logical NOT. If we apply the value, any value, for example 2, 3, which is not 0, then it will evaluate to 0. And if we apply the value A and C, means that both of these values are not equals to 0, then it will also evaluate to 1. And but if we give the value that is higher in peak, for example non-zero value, then it will logical not operator will give the value to unknown. So let's simulate it. It will take a little bit time to be compiled. So here let's come towards the logical operators. These are logical and, logical or, and logical not operator, that is generally used as a sign of exclamation. So the logical operators are logical and, logical or, and logical not are the logical operator evaluates to either one, false, and unknown. Means that if any of the value is not known, then it will give the x as an output which is unknown. But if the statement in the logical and, if any of the one input value is 0, then the logical AND will evaluate to 0. But on the same side, if the logical OR operator is applied, but only one value of the input is 0, then it will evaluate to 1. So if the value of high peak value is given to this, let's suppose it is non-zero value, then it will evaluate to 0. On the other hand, if the value of non-zero value is applied, then it will evaluate to unknown. So these are the general logical operators that are extensively used in the FPGA program. So let's run this simulation. So after clicking the simulation, the process like here will be appeared, and so it will take a little bit time to be compiled. So let's wait. So as you can see that it has successfully compiled, there is no any error. So let's go towards the university VWF, then click OK. Then again repeat the same process as in the previous node finder, and then list, and then input. Just transfer all these inputs to the graph. So here you will see that A, B, C, D, E, F. You just only click on the inputs and output groups. So here is the nodes, and here is this. So we will take only the unsigned decimal values, so converting them into unsigned decimal, because we only need 0 and 1, 0, 1. So I will just convert these all values to unsigned decimals here. Actually these values are already given in binary form, 4-bit values. Here we go. So here are the values that are totally converted. So if we go towards here, the A is equals to 2, B is equals to 0, and C is equals to 4-bit hexadecimal. So we will again convert that value of C into 4-bit hexadecimal. So let's first apply to A is equals to 2. So here will be the 2. Then U is already 0, B is equals to 0, and then first we will convert it into hexadecimal, and then we will apply the values to this 4-bit hexadecimal value. We will apply X, which is generally unknown, because here is not any value is given, so we will only apply the hexadecimal value that is in 4 bits. So this is the hexadecimal value X, which is unknown. So let's perform the operations on this. After saving the waveform, you will see that the simulation will be started like this. So here you can see that after applying 2 and 0, and this C is equals to hexadecimal 4-bit value. So here you will see that D is equals to A, logical and B, means that if any of the one value is 0, then it will evaluate to 0. Here you can see that the value of 0 is appearing. But A or logical or B is equals to 1. Again, the logical node of A is equals to 0, because the value that is non-zero, the logical node of that value will be 0. And it is equals to, here you can see that the value of G is equals to A logical not C means that the comparison is in between 2 and the 4-bit hexadecimal value that is unknown. So the unknown evaluation will be evaluated to 1. So here the 1 is appearing, and the last but not the least, the output of H was equal to the logical not of C, means that the C was unknown value, so its logical not will also be equals to unknown, that is in the form of X. So here was the work for logical operations. So now move on to the Rtl view. You will see that this is the Rtl view for this. Generally, the combination of AND gates, wide, NOR, and this is comparing all these values. So now let's move on to the logical operators that for the exercise. We will perform the exercise as well, and I will let you explain what this value will evaluate to. So this in exercise we will learn how these all operators are working. So I've already made the code, so I have to just uncomment this section, and you will see that the value is appearing. So again, commenting the lower section. So here is the exercise, and the module is logical. So I have to just change this name because I've already named here the lab 05 HASSAN. I will again name this lab 5. So it will run. So these are the total number of the inputs. Input is 3-bit value. The output will also be 3-bit value. So again, the same process will be repeated, but here 67 not means that the logical not of 67 will be 0 because non-zero value has a logical not operation. After performing this operation, this value will be equates to 0, and this is the A and 0 and 1 means that in logical AND operations you will see that the logical AND if only if one input is 0, it will evaluate to 0, and here the logical of 1 logical or 2 means that one logical or operation, if any of the one value is 0, it will evaluate to 1, and if both the values are 1, we will see that what will happen. Here will be the logical AND of 0 with logical AND logical OR of 0 with logical AND of 1 with logical AND of 1, and here the answer is the logical OR of this answer with the logical not of 1. So let's simulate it. So here you can see that it is giving some errors. We will see what's happened here. Actually, we have the names here. So we will see. Actually, here you can see that it is not closed in the brackets as we have closed in the previous ones. So we will close it in the brackets as well. So I closed here. Again, I have closed it in this bracket as well. This one and this one and this one. So one mistake that I've done here is the AND module. I have not written here, so I will paste the AND module because when you don't write AND module, it will continue to read the code. So here I'm going to write AND module. Again, I will compile. So let's see what's happened. So here it is successfully compiled. So now we will move on to the university VWF, again repeating the same process to evaluate the output values that what it is giving. So inserting the nodes, node finder, and then list. Here. Clicking OK, and then here. Again, we will convert all these values to the unsigned decimals. So I will convert it into the hexadecimal, but this value will remain x, means that it is unknown. So we will compile here. Now, before starting compiling, we will assign this value a is equals to 2. So let's give it the value 2 and then click OK. This value will be 0 and this will be x for bit hexadecimal. So now start compilation, then save. So here you will see that the unknown is appearing at the, because the sorry, here is the unknown already. So the D operation was the logical node of 67, means that the non-zero value has the logical node operation equals to 0. So it is 0 as expectation, and the value of E, we were expecting that it should be equals to 0, and here we go, it is also equals to 0. And here you can see that the logical, this was the logical AND operation of A with 1 with 2, means that logical AND, one logical AND 2. Here you can see one logical AND 2. So it is equals to 1, means that both, at least one of the value is equals to 1. And then the logical NOT of 0 with the 1 logical AND of 1, and then with the logical NOT of 1. So here you can see that it is also giving us the value of. So this is the second question for this exercise, that what will be the value of gamma is displayed if the following module is run. So here you can see that the module is alpha to beta and gamma. The different there are the different integer values that we have given to that. Instead of giving them and dividing them into the bits, means that 0 to 3, I have only assigned these values. So here you will see that the input is only 1 and there are the two outputs. Input is beta and alpha 2 and gamma is the output. So we will only apply beta is equals to the 1 bit 0 value, and then we will see that what is the behavior of these operators. As we discussed earlier, alpha 2 is equals to the logical node of beta, means that the beta value is 1 that we have applied, then it will be the opposite of this 0, means that it will be 1. So the alpha 2 is equals to 1 now, and then alpha 2 logical and logical or the and beta, means that 1 logical or 0. So as we have already discussed that the if and only if only one input is at high logic state or at 1, then the logical node of high logic state will equal to the 1. So let's see its RTL view, University VWF view. So here you will see that I have applied this value is equals to 0, and then after simulation you can see that the higher logic state for 1 is appearing, so it has proved. Here the RTL view for this is this, means that we are applying the beta, and then after that alpha 2 is equals to the logical node of beta, and then alpha and gamma are appearing at the output, means that it is 1 bit value, that is 1.
So here are the rational operators. We are doing exercise number 2. The rational operators generally here the key symbols are greater than or less than, greater than equals to, or less than equals to. So these operators, just when we apply these operators, then the value of 1 will be shown at the output if the statement is true, and false will be shown only in the form of 0, and if the value that is not known, the unknown value will be equals to x at the output. So these are the inputs and the outputs, means that a, b, c, d is the 4-bit value that we are applying at the input, and the 4-bit value is obtained at the output, that is a, f, g, h. So assigning these values, the a is equals to a is lesser than b, and here you will see that a is equals to 2 and b is equals to 5. So this equation is true, so it will give us the 1 output. So going towards the f, you will see that a is equals to b is greater than b. So here you can see that b is greater than a, so this is the wrong statement. The 0 will be appeared at the output. and then we will see that the A is equals to or greater than C, means that only one situation is proved, because there is an equal sign, so it will also evaluates to 1, because A is equals to 2 and C is equals to 2, both are equal, and then the H comes the 4-bit hexadecimal value which is equals to X, and X is unknown. So D is unknown and A, so the comparison doesn't meet the criteria, or so it will give us the value that is unknown, so the output in X will be appeared. So here is the University VWF output. You can see that I have applied 252 and hexadecimal number that is unknown. So the output is really as was expected. Here you can see that this was 1, means that equation was true, this was false, this was true, and this was unknown. So the at output 101 and X should be appeared as we were expecting. So after simulation you can see that 101 and X is appearing. That is the approval of this statements that I've used in this code. So now I'm going to locate the node in RTL viewers. Here you can see that the circuit will be appeared. Takes a little bit time, so here you can see that less than 0, greater than 0, or these signs are appearing. This is the RTL view for this. So
equality and the case inequality. So here I am just declaring the lab lesson, and there are the total number of the input values, and the input values are 6 in number, and the output values are 5. Input values are 4-bit values. So these are all the values that I have to insert in the University VWF program. So here I am assigning this A is equals to B. The logical equality will equate to 0, where A is logical not equals to B. Then this is logical equality. C is logical inequality, and then D. Then this equals to X, because here the D is unknown. One value of D is unknown. So this answer should be appear in the output while we simulated 0x1 0x. So let's see what's happening in the output. So as there I have already simulated the experiment, so you can see that the input values are these, and 0x1 0x is appearing in the output. These line at the base is showing the 0 logic state, or the 1 logic state is shown by this line. Also these are shown by unknown, because any value can be appeared in there. So this is the Rtl view for this entire. So it is the exercise number 3. This was the question that was assigned to me. What are the values of these? Irrespective of the values inserted, we have already given the values. So these logical operators will equate all these values and give us the output irrespective of the values that we have inserted in A, B, C, D, E, F. So here is the University VWF simulation waveform. Here you can see that I have not inserted any of the values, and after simulation you can see that 1, 1 and 0 and 1 logic state is appearing here according to the equations that we have used here. So this is the output of the Rtl viewer. Now we will come towards the bitwise operators. These are the operators which is generally known as negation and or, and this is the symbol for exclusive or, and this is exclusive NOR gates. So these are all the inputs and the outputs, and the name of the lab that I've already discussed. These are the 3 inputs, 3-bit values, and the output are also the 3-bit values. So these operators just compare the values and perform the operation bitwise scenario. Means that it will take 1 bit from here and 1 bit from here and perform the operation, just give the answer, and then evaluate the next bit and also the next bit of B, and then perform the operation and then give the answer. So here you can see that D is the negation of A, means that 0, 0, 1, 1, 1, 0, 0, and the opposite of 1, 1, 0, 0 is 0, 0, 1, 1. So these all the outputs will be shown below. Here is the exercise number 4 that I have already inserted here. So we will cover it in this video. Here are the J and K and L outputs for these. So here you can see that there are a total of 8 outputs and irrespective of the values that we have inserted, these three operations will be performed, but these operations will be performed on the basis of the values inserted above. So let's see what's happened. Actually, I've already made this, so here you can see that actually this is the negation of this one, and you can see that it's appearing here, and all the output waveforms are there. Here the D is missing, so let me insert, because the negation of A is equals to D, but D is not appearing, so by mistake I not inserted. Again, go towards the node. A, B, C, and then the D comes. Insert node finder, and list. Here we go. The D is here, and then click OK. So drag it onto the bottom of the C. So here is the D. Now again simulate this file. You will see that it will take a bunch of time. So here you can see that this is the value for A, and D is the opposite of this, means that D is a negation of A. So you can see that it's appearing, and after that all the exclusive or exclusive NOR gates and all the operations are performed. So here was the entire output for these three inputs, and the RTL view for this is like this one. Here are the four AND gates for no exclusive NOR gates, and these are exclusive OR gates. This is for, and this is NOR. So all these 5 types of the gates are performing the operations that we've inserted. Here we go towards the reduction operators. Actually, these operators are working on only the single values that we taken as input, because these variables just perform the task by selecting only one bit and then perform the task on the one bit and the second bit, just like as this value is 1111. So this AND operator will do the work as 1 and 1 is equals to 1, and then it will perform the operation on 1 with the answer of both of these. So 1 and 1 is equals to 1, and then answer is 1. So it will perform operation on the next one. After that, 1 and 1 is equals to 1, and then 1 and 1 is equals to 1. So this will evaluate 1. Then we will take OR of B. OR operator is generally like the OR gate, means that if only one input is 1, so it will give us 1. So here you can see that 0 or 1 is equals to 1, and 1 or 0 is equals to 1, and then the answer 1 or 1 is equals to 1. And then we go towards the exclusive OR operation. So exclusive OR operation generally do like this: 0 or 1 is equals to 1, and 1 or 0 is equals to 1. Then 1 or 1, sorry, 1 XOR 1 is equals to 0. So this is the operation that it takes the 1-bit value, and next by next operation it performs. So we will go towards the simulation waveform. Here you can see that 1 1 1 1 and 0 1 0 1 are the inputs, 0 0 1 1 also. So it will perform, it has performed the task as we were expecting. The values are here like this: 0 0 0 1 means that it is 1. Here it is also 1, and here it is 0, the binary value and the unsigned decimal values. So here is the RTL view for this one, and here will remain 0, and then this will give the value as 0 1 0 0. So this is the working of the shift operator, and then we are going to perform the exercise number 6 that is indicating that 4-bit value, and this is the equality operator, and then 4-bit value is jumping from right to left to right by the 1. So here we will see that the value will shift from this side to this side. So this will become 0 1 0 0. Similarly, this will become 1 0 0 0. So this value will be equated by this one. So let's see what's the answer, please. So here you can see that it has successfully compiled. So we'll repeat the same process as in previous ones. Edit, then insert node finder, list, and then we will select by pressing the control button. So these are A, B, C. Actually, these values are not appearing because we have not declared the other values. So we will have to go back, close all this. So here you can see that the values remaining are not declared, D and E. So we will declare these values here, D and E. So again compile. So here we move on to the shift operators. Here you can see that I have successfully compiled this by choosing the inputs from the code. So here is the University BWF simulation waveform. As you already know that I've given only one input, so the shift operator has shifted one from right to left side. So you can see that 0 and 0, 0 is appearing and shifted these ones from left to right by the 2 jumps. So it has given us the exact value that we were expecting, and the D and E were the values of these equations because it is performing the logical equality, and then first it is performing the shift operations and then performing logical operations, equality operations. So here is about for the shift operator, and its Rtl view is just like this. So the next and the second last work is the concatenation. Its key symbol is generally shown by the comma sign. So here we will see that I have applied the input of 1-bit value, that is A, and the input of 2-bit value, that is B, and the input that is 6-bit value. So the output is of 4-bit value. So here we will see how this is working. Generally, the work of the concatenation is to combine the two inputs without performing the operation in it. For example, if I am going to combine 1 and 2, so here A comma B is equals to the 1 will be combined with 0. Means that the value that is appearing at the first will be combined at first. If A will come at the after B, so it will be 0, 0, 1. So here you can see that this answer should be appear at the output, but we are taking C. Actually, the output is 4-bit value, so we have to arrange C and A in such a way that it gives us a 4-bit value. So we are taking from 3 to 5, means that it is a 3-bit value, and then this is 1-bit value. So 5 to 3 means that these values will be taken from this 1, 0, 1, and then the 1 will be combined with after that. So here you can see that 1011 is appearing at output. So in order to prove this, so we will see the output here. I have applied 2-bit zeros and 101001. So you can see that the 0100 and 1011 is appearing at the output. Here is the Rtl view for this. So here is the second last experiment of this entire lab, and then we will complete exercise number 7, and then we end. So replication comes. Replication is generally used alongside concatenation to repeat the number as many times as specified. So we will see that the input is A is applied. So we are taking the input A, that is 1-bit value. The output is 4-bit value, that is C. So generally the one thing we have to do is to just write the 4. If we want to repeat it 4 times, means that we are converting this 1-bit to 4-bit, so it will repeat 4 times. If I write here 5, so this A will repeat 5 times. So here we go. Let's simulate it on the University BWF. We will see that what happens when we are going to perform concatenation in PC. Okay, we have to just input A and then output group transferring. Okay, then okay, here you can see that I will apply 1, and then we will see what's happened. here you can see that the 1 is concatenated 4 times, means that 1 is appearing at the output. Hence this code is true. Now this is the Rtl View, because we are taking the input 1-bit value and then output is 4-bit value. Yes, that one is repeated 4 times. So here's the exercise number 7. Last but not the least, the question was how does D value evaluates in the following. So here you can see that the input is 1-bit value and the B is 2-bit value, C is 4-bit value, and the 9-bit is D, because for care we have just take it, otherwise I can also take it as 8-bit value. Sorry, it's a 10-bit value. So here you can see that the C is equals to 4A, means that A is concatenated 4 times. The input A is 1, and it means that I'll just comment here, means that the value we evaluate is 1 and then B C B, means that it is combining. So after when the A is replicated 4 times, then we will concatenate these 3 things together and it will evaluate to, means that B is 0 1 and then 0 1 will come in the front and then C will come and then 0 1 will come. Then this will evaluate to this value. So let's see what will happen in the simulation waveform. So you can see that the tetra 1 is appearing here and 0 1 is coming in the front and 0 1 is coming at the back of this number. So you can see that these two values are the zeros